Okay, all right, here we go. Sorry about the inconvenience. Hopefully everyone's looking at my page. I've kind of got a home office, so I've got computer, I got a big screen here. So, pardon me if I'm not kind of looking face to face here so I can focus on my big screen. Hopefully everyone can hear me without me yelling too loud and disturbing everyone else. But sorry for the inconvenience. I got a couple of sick kids today and my wife worked, so um, that's why we are here today. Like I said before, and you can see the announcement I sent this morning. I like being face to face, but I didn't want to cancel class, so I wanted to kind of talk about presenting this forum here, even though it's probably not most optimal and probably not optimal for me. Most importantly, um, most importantly here. So what we're looking at here is a upcoming schedule we're looking at. So today we're going to talk about predictive analysis. We're going to hear the word regression. Don't get too scared by it. We're going to start to look at relationships between independent variables and dependent variables and look at measuring these using y equals mx plus b, which is the formula for a line. And this is stuff that we've kind of had from math class, but instead of going over 1, 2, 3, 4, we're going to go over particular units, whether it's median household income versus age. So these axes are going to have units, and we're going to look at multiple axes if you can visualize those. Next week, we're going to talk about spatial interpolation. Basically, we have known points, and then you fill in all the missing pieces. Week after that, we're going to look at spatially weighted regression, and then we're going to start talking about circumventing issues in geostatistics, because last week, we talked about some of the challenges in running two-tailed t-tests as well as clustering. Clustering looks at the mean. What is the definition of high? Values really above the mean or below the mean. So if we deal with some of these extreme outliers, we're going to run into issues. We're going to have the same problems here when we run correlation. And then people like me reading papers, or people who are really good at statistics who read papers, they're going to really call you out on some of the methods there. So I want to make sure when we talk about circumventing issues in geostatistics, which we'll cover on the 13th and the 20th, that we kind of cover, dot our I's, cross our T's with a lot of our methods that we're doing here. On the 20th, we're also going to prepare for the final exam. Following week, we've got Thanksgiving week, and then all assignments are going to be due at 12 o'clock noon. Now, some of them may be late already. I've marked some late. But all assignments and the position paper will be due at 12 o'clock noon. And then the final exam will be given on the 4th of December during our regular class time on a Wednesday. For online students, I'll open it up from Tuesday through Thursday. And like we did with the midterm exam, you can take it at any location. Just make sure it's taken by yourself, and because I submit grades to the registrar by the 6th. So I don't care who's graduating, not graduating. I submit them all so that if someone's not on my list of graduates, I've got everything covered here. Couple things that I did want to cover are some things out there about jobs. I know some people are looking to enter the workforce. We got a couple of other big events coming up too that I'll mention here. But a lot of times people say, I want a job, because the most important thing when you go to school or whatever is getting a job. And we're going to have some students on the 21st, which is a Thursday, come and talk to us about the work they do in the workforce. A lot of them, I think all of them are local. Department of Environmental Quality, DOT, and one works for the city of Durham. These are all students in our department. They all are going to talk about what they do. They all were sitting in the same seats you are in 1227 in the classroom, and now kind of are out there doing some really neat things. A couple of really good places that I go to. One of them is called GJC. This stands for GIS Jobs Clearinghouse. This has been around for decades. I think I got my first GIS job from here in like 2001, 2002. This just has a big list of GIS jobs. You can see a lot of Esri. You can see, we've got utilities, conservancy, environmental science, We've got GIS developer, which is fully remote, geologic and economic survey. We have city jobs. We have tons of different GIS positions. I would venture to guess that the city of Durham probably has about 8 different GIS people, and we're going to be speaking to one of them on the 21st during GIS Day. I'll post announcements for that. Our department's going to be hosting lunch, and I've also made some requests, asked some of our students to present like 5-minute short presentations on some of the work they're doing in our department before we kind of segue into what our professionals do. And, we've got a couple of them here. This is the Waterworks and Sanitary Board. One of our students that's going to be speaking, he maintains all the sewers for City of Durham. That's all he does. That's his whole space that he lives in. So we can, click on this. You can see how to apply. We can see the salary range, $58,000 up to $92,000 here. And this just talks about everything here. Maintains, edits, controls quality of board's GIS database, digitizing, coding, verifying accuracy of data, enters data into GIS database, mathematics, coordinate geometry, cadastral mapping. This word cadastral is just big fancy word for parcel mapping. Corrects, evaluates field data for use by other staff. We do fields. And so combined with this, some of our GIS classes and our field mapping class, I think you'd be really well positioned to do something like this in Montgomery, Alabama. Knowledge of GIS, coordinate geometry. One of the things is that if you don't know, what coordinate geometry is, go to the GIS training site and look it up. And there's probably a GIS course in the Esri site that we all have access to related to coordinate geometry. Knowledge of geography, cartography, how to make maps, ArcGIS Online, which was some of the things that we're doing here, engineering plans, but these are really neat things here. Survey 1, 2, 3, and field maps. This is what we talk about in our field mapping class. This is a graduate level class. We're going to have a field day with this. Proficient with CAD. I'm not too good at CAD, but I can figure it out. And geographic information, GISP. Those are some professional organizations that you can belong to here. But these are just some of the jobs out there. I'll show a couple other places that I like to go to here. But when we start looking at what are the jobs out there, this is where they're living here. GIS specialist, City of West Fargo. We can see everything here. Bachelor's degree, 2 years of experience, valid driver's license. This role has a starting wage of $27.28 an hour. How many $1,000s a year is that? Who's going to pay you $27 a year? How much pay is that?
It's like around 50-ish.
Yeah, a little more than 50. How many work hours are there in a year? How many work hours are in a week? 40? Work weeks in a year, not holidays?
160 times 12.
What's that?
160 times 12, so what, 1,600 plus 2?
Yep, it's about 2,000. So
There you
that's
go.
what we're looking at right there. Just double it and throw some zeros on, because that's about 55,000 a year. 55,000 a year to start working in West Fargo, North Dakota. But we can see some of these up here. I saw one that paid really well, but then when I looked at it, I think maybe the Montgomery, Alabama one. But I saw some of these that were really pretty good paying, but then you looked at the cost of living and you're kind of, okay, now I see why, so you can get an idea as to some of these places that get really pricey really quickly, and your money doesn't go as far here. All right, this is a great job, GJC, if you're ever interested. Not once in a while, every so often we get some North Carolina jobs that come up here. This is obviously Indeed. Go to Indeed. I think this morning I typed in GIS in North Carolina. These are some things that popped up. Brazil Management Company, GIS drafter, director of operations. So my wife works in the field of telecommunications, so they're increasingly starting to use GIS to attribute all of their utility lines. Like I say, probably every so often, she'll get a call that someone has dug up their utility lines, and it's basically because their old GIS systems are, their old GIS data is obsolete, or the people looking at them are looking at paper maps, which become obsolete the second you print those out. Project managers, field techs, here's one in community development, pay information environmental consultant. So this kind of ties in with some of the environmental science that we do here. Part-time instructor for marine GIS, that's not applicable here. But these are, I think, some good positions here, tech positions. And then another one that I really like is USA Jobs. USA Jobs, they're government jobs. They probably don't pay as much, but I like them because of the stability attached to them. Some of these companies here, you work on contract by contract, basis here. So you might be working for ONUG Communications Incorporated, working at the airport, doing all of their GIS, but the airport or the state, they hire someone else to do it in 4 years when that contract runs up, and either you get hired on, or guess what? You got to go look for a new job. So the volatility attached to contract jobs like Davy Resource, another one around here is called Pike. Hit or miss from time to time. And those are things you kind of go into a job, thinking about. But there's a little bit more stability with some of these. This is an interdisciplinary GIS specialist. One of the students who's going to be working, who's going to be presenting at GIS Day in November. He worked for the Army Corps of Engineers down in Charleston, South Carolina. He's from Wake County. Ended up getting a position in Wake County, and he's got a really interesting story to tell. So maybe after the break, I'll kind of talk about him a little bit, because he's got a really good story to tell. Supervisory GIS in Honolulu, starting at $107,000 a year. That looks good, but I've been to Honolulu a couple times, and $107,000 isn't going to get you that much, and unfortunately. These are some interesting things. Emergency management specialists, especially with the integration of drone technologies, but emergency management specialists, on-call, plans, guides, working for FEMA here. We do some work with NASA, and there's some really interesting things that people, they're on call a lot. Working for the military, Fort Bliss, geospatial scientist, Department of Justice in Quantico, cartographer, U.S. Department of Fish and Wildlife. So you can see where these are. This thing, GS, stands for Government Services. So you get different pay grades depending upon where you live. If the cost of living is higher, so you can say I'm a GS 12, GS 7. You can see down here for your project manager. And then you can start to see some interdisciplinary with biology, ecology, environmental science, and whatnot that kind of bleed into biology, environmental science, and some of the other classes that we offer here. So I just thought these were pretty neat positions here. Take a look at these. There's nothing wrong. To me, the toughest job that you're going to get is your first job. And so once you get that, it doesn't matter, your GPA or any of those other things. Your future jobs are just going to be based on your last job and, recommendations and all those other good things. Okay, so today we are going to talk about predictive analysis. It'll kind of work the same way. So I'll talk for a little bit. We'll go for a break, and then we'll start working on the exercise. If I were to look here on week number 10, there is not an official exercise attached to this. So we're going to do we're going to run some of the regression. I've actually stored an example here in Excel. So we're going to kind of play with Excel a little bit, expand our skills a little bit, but we're going to have an Esri assignment and a reading attached with predictive analysis. I want to make sure we understand how to interpret the results. These p-values, to me, I just look at the p-value. The lower the p-value, the more different it is, the more significant it is, if that's what we're looking for. Maybe we're looking for things that aren't significant, or we can't say they're different. And so all those kind of funny wordings that we talked about with our two-tailed t-test and even our clustering, we'll kind of revisit when we talk about circumventing issues in geostatistics. We're going to work on the case study, but I also have some good textbook material of statistics with geographic data. I've got a couple of videos where I run some very simple linear regression in Excel, and then we do some using ArcGIS Pro. So that's what we're going to do after our break. Okay, well, hopefully everyone can see this, but we're going to be talking about predictive analysis today. And I'm making sure I'm recording everything, so we got it. All right, so predictive analysis. These are just some examples here because a lot of times people want to know, well, what are we trying to predict? I'm going to use words like independent variable and dependent variable. So I want to make sure that, these are things that resonate with you in, math class or whatnot, that you've heard about before. So we're not really doing anything too new. We're just applying it differently. So some of the examples of predictive analysis are which variables best explain factors of bear sightings at the quadrant level. So we're kind of revisiting this bear paper. We create these quadrants. And remember why we create quadrants? Quadrants are just little evenly sized squares. There's some good things about quadrants. There's some bad things about quadrants. Quadrants aren't very practical when we're doing things with crime, populations, because we don't collect data in nice, pretty little squares. We collect them in block groups. We collect them in block groups and everything else. Which variables best explain age-graded heart disease death rates at the zip code level? That's what we're going to talk about today. Which factors best explain by-mail voting rates in North Carolina? You're going to be doing that for reading number 4. How about, here's a simple one. Can the 2020 by-mail voting patterns be explained by the 2016 by-mail voting patterns? So we did this paper and we'll kind of we'll look at this paper. I'm pretty sure I've got it open here. Reading number 4 is the paper that Dr. McGeehan and I wrote entitled A brief statistical and geostatistical survey of the relationship between COVID-19 and by-mail voting in the 2020 North Carolina general election, because we have an election coming up, which will hopefully be over soon. But we were looking at what factors impacted by-mail voting rates for the 2020 general election. So that is going to be our dependent variable. Just kind of thinking about these things, getting these things kind of up there and thinking about these. Like I said with this paper here, most of the paper was just data preparation. And so when we get into data science class next semester, and if you take it, I'd strongly suggest it because, well, I don't want to have to teach undergraduate classes. So I'd rather you take my data science class. We're going to go through some of this data, look at it. I think we're just going to go through it for an entire county instead of the entire state. But what we do here, we look at a dependent variable where we try to figure out these are our patterns attached to what explains this pattern here. Is it age? Is it race? Is it ethnicity? It'd be really silly if I looked at the map and the 2020 rates looked exactly like this. And when we were reviewing the paper, someone said that. You better make sure just the patterns attached to 2016 aren't related to 2020. That would be kind of silly. And I go through all these different machinations to figure out what explains it. It's race, access to transportation, all income, all population density, all these things, when it was just the same exact patterns as before, because each of these zip codes is going to be a data point, okay, like 5,7, but these things have values, percentages, incomes, everything we have attached to this. And I'll kind of go back and revisit this because a map like this, we remember this. Remember this map right here. But we're going to be looking at this table right here when we run something called OLS, ordinary least squares analysis, where we're going to look at all the different factors that try to explain by-mail voting patterns. Is it population density? Is it median household income? Is it poverty? Is it percent minority? Is it COVID rates? Is it change in COVID rates? Is it Democrat, Republican, or independent? So what are the different factors attached to these? And so that's, because I've talked about this paper before, but I want to kind of go back and revisit this, and that's what our reading number 4 is going to be. So when we do this, basically this is what regression looks like. Now, when we do 2D regression, we just look at, is there a relationship between height and weight? So if we measure someone's height, this graph basically shows the taller people are, the more they weigh. And we have this line here of best fit. So we'll talk about, we can create this line of best fit. And believe it or not, when we make a scatter plot in ArcGIS Pro, we can click a little button and it'll give us that line of best fit, or give us the equation for that line of best fit. Because this says weight in kilograms is equal to negative 114.3 plus 106.5 times height. This looks a lot like y equals mx plus b. Y is your dependent variable. So y is this axis right here. X is your independent variable, which is the x-axis right here. So instead of going over 4,7, we go over 1.5, 60. And this is a person right here, a data point. Now, what are we going to be graphing? Zip codes, okay, which have age and income and COVID rates and all these other things that we can map. So we have people above the mean, we have people below the mean, but we're going to talk about this line of best fit. We're going to look at something here called an R squared. But when we think about it at the most kind of fundamental level, think about y equals mx plus b, okay? Y equals mx plus b. This is the equation for a line, and we're going to go through and do this a little bit in Excel. Here's one: time watching TV per week versus your grade. And you can see here, as your time watching TV viewership increases, your grade goes down. So this is what we call linear regression. We're going to do a couple of examples from some students, actually a student who's taken this class here. But we look at linear regression. It attempts to explain the relationship between two variables with a straight line fit to the data. Now, this is linear regression. We're going to have something called multiple regression. Multiple regression is going to be hard to visualize because we're going to have other axes. And on a flat surface, it's hard to visualize multiple axes like 3D and 4D and 5D. It's difficult to visualize, but they exist. Correlation provides the strength and direction of the relationship between two variables, their relative position. It provides corresponding values of variables. It's an estimation of the linear relationship between a dependent variable and an independent variable. And there are variations to linear regression. So instead of putting in a y equals mx plus b, we can fit it with a curve. We have something called logistic regression. But basically, we have an equation sitting right here that looks a lot like our y equals mx plus b that fits it. We get a little bit more fancy where we can increase this r squared a little bit. Now, one of the projects that I've really liked that we did before was EOG scores. And those of you who are parents, we know all about EOG scores, end of grade scores. And we had a student who wanted to see if there was a relationship between non-passing EOG scores, which you see on the left, and school attendance rates. So we went and got all of the non-passing rates. We got all of the attendance rates to see if there was a relationship between school attendance and non-passing or passing rates here. And we mapped these because at the end of the day, these are two maps. And one of the challenges of making a map is they get increasingly difficult when we start to put multiple variables on top of each other. I hear people discuss, I want to map this and this and this and this on the same map. Well, it gets really hard. Those are some of the challenges that exist with GIS, and in particular cartography, the art and science of making high quality maps. So we put these two maps side by side. And so you can kind of see here, okay, there's big dots here, there's big dots, small dots here. Okay, there's a big dot here, small dot here, big dot here, small dot here. But you can kind of see some correlations, but we can graph them on each other here. So now we can see here This is percent attendance, and this is the, dozen or, 8 or 10 different middle schools in the state where we have percent attendance. As it increases, the non-passing or failure rate decreases, except for this one here, Shepherd Middle School, which is right around the corner from campus here. But for the most part, you can see it kind of goes in this direction here. The slope is negative. So as attendance increases, our failure or non-passing rate decreases. And so we have studies right here using empirical data. Empirical means measurable data that we can take from North Carolina Department of Public Instruction right now. And we could probably within the hour make a map and make data that looks like this to reinforce the point how attendance impacts EOG scores. But like I said, I'm the where guy, okay? Why, that's a much bigger issue here. Here's another one here. This is convenience store accessibility. And so this is a map here at the block group level here. So you can see our little block groups right here. Within these block groups, we've got age, income, race, education, tons of different variables that are collected by the census within each of these. So that's why those quadrants aren't very good unless we're kind of working with other data that's not encapsulated within quadrants. But I've got a map here that has convenience store accessibility. And so I've measured how far it is in kilometers to the nearest convenience store. I forgot what measure that I used previously. So you can see over here, kind of the east side of the city, they have much better access or availability to convenience stores. These other darker areas here have lower access to convenience stores. And what I did was, when I map it, my income on my x-axis, my distance to a convenience store on my y-axis, do you see a pattern here? What happens as income increases? They get further and further away from convenience stores. Do you think that's an accident? I don't either. Okay, I don't either. And we're going to look at some measures here that discuss these. I can put in a line of best fit, and this graph, this line of best fit, is what we call a positive slope. Okay, because we're going to talk about positive slopes because we just looked at a negative slope. We have a positive slope, negative slope, or no slope, which basically means no correlation here. Now we're going to look at a test here, a regression test, just a linear regression that we can run in Excel that tells me if I had 67 points right here. Because remember, this map right here, this is spatial. This is a spatial map here. And so each of these block groups is a data point where its income is on the x-axis, its distance to a convenience store is on the y-axis. Now, if I had 67 points right here, what are the chances I threw 67 points up onto this screen and it appear like this? Because look, you're missing stuff down in the bottom left, bottom right. You're missing stuff up in the upper right, upper left rather. What are the chances we have a pattern that looks like that? Very, very, very small. And it's kind of like our p-values. You get p equal to 0.000001. We've got some statistical significance there. Yeah. Now we have different types of regression models. We have linear regression. This is the fitting a line to y equals mx plus b. We have nonlinear. We can run these in Excel, not only Excel, but we can run these in ArcGIS Pro as well, where we can fit to a curve. Remember the curves for a parabola is equals like y equals ax squared plus b. Okay, so it gets a little bit more complex. And then we have multiple. I'll talk a little bit about multiple because it gets really difficult to conceptualize when we fit things with a plane, and then nonlinear where we fit things with kind of curvy things right there that have really complex equations attached to them. So our equation is y equals mx plus b. This is straight from math class. Okay, so our predicted value, and you see the little hat right there, so I call it y hat, equals the slope times x plus a, the y-intercept. So if you want to just say y equals mx plus b, you can say y equals mx plus b. And so we can see this curve, this line of best fit right here, and we can see how far away each of these points are from the actual line itself. Because we know in reality, in reality, they're not going to fall exactly on the line. There's a lot of other factors that impact this phenomena here. And we're going to look at some of the phenomena that we've already looked at, explored previously. So our predicted values like y hat expected equals 20 plus 1.5 times x. And we can just fill in, for vitamin D equals to 95, we can pop in wherever we see an x, we can put a 95, or I'm sorry, 9.5. 9.5 for these moles, pop it in and do the equation. Okay, so we can just fill in, and I'm gonna run this here in Excel in a little bit as well. Get an idea as to what it looks like here. So this is how we populate a linear regression model here. So these are called our observed values. Everything on the line is what we call our predicted values. So all these points here, whether it's income versus distance to a convenience store, EOG failure rate versus attendance, these are what we stick on a Cartesian coordinate plane, essentially, a multi-axis plane. So we can put these onto a plane here. Now we start to get these equations right here. But we start to get these equations right here with these observed values here. And I'll kind of mention the equations a little bit because we let Excel go and run it for us. Because when I think about this, can I draw a line through these? No. Okay. What's the line of best fit? Okay. What's the line of best fit? Timer on this thing here, so that kind of stinks. Okay, but what we do here is we do a best fit. We have this big equation, we sum the squares, the differences, because we know the values, and then we know what we need to calculate is the m and the b from these known values. And so what we need to do is kind of offset all of the positive and the negative. So it's got to be somewhere in between these lines of best fit. So line of best fit means the difference between actual y values and predicted y values are at a minimum. Okay, if I kind of go back to here, let me go back to this one here. I swear I know what I'm doing. Come on, computer, come on. Okay, I go back to this one right here. Okay, this is my line of best fit that's sitting right here. If this line of best fit were up here, it'd still be positive, but the distance between these points and the line would not be minimized. So this line of best fit, all we do here is we put it so that the distance between this line and these points has been minimized, because we move it all the way down here. Well, it's still positive, but we haven't minimized the distance between these points and each of these 67 points and the line that we have there. That's all this equation does. And so when we run, sometimes we use the term OLS, ordinary least squares, LMS, but we run the least squares. Okay, because when we calculate it, and it kind of harkens back a little bit to our variance and standard deviation, right? What is variance? How far away something is. So we're not too far away from that. And basically what we want to do is minimize our variance in a very general term between the line, the predicted value, and each of these points here. So best fit means the difference between the actual y values and predictive are at a minimum, but we need positive differences offset negative differences. Okay, we need to have positive differences. And so we draw this line right here so that these values are minimized if we add them all up or square them or whatever we do here. So we have this sigma. This sigma means add them all up. It's sigma notation, add them all up. So add up this one plus this one plus this one plus this one, because you can go through and run multiple iterations, especially with this extremely powerful software. We have something called stepwise regression. That's usually that's typically a multiple regression, where that it runs multiple scenarios, thousands, millions of times, so that we can minimize this offset right here. So we have a prediction equation, we have our slope, we have our sample y-intercept. This is how we calculate them. We don't, once we start getting into this kind of starts to ring a bell right here, doesn't it? Okay, the x of I minus x bar. What does this x bar stand for? Average. Okay, just like we did with cluster analysis, this is average. So I'm not a good enough statistician to figure out, what are the impacts of outliers on lines of best fit, but that would be a really good subject for someone in the future. This is how we calculate it. So we start to add things up. Oh, yep, ignore. This is the computation table we have, because at the end of the day, even in Excel, you can see we're going to do this in Excel today. This is what we get. This is a criminal justice example here. So we get drug calls versus drug arrests. So can we predict the number of drug arrests in a zip code or a neighborhood based on the number of drug calls that it receives? And they came up with this equation right here, y equals 1.0193x plus 4.460. So if I were to plug in 0 right here, plug in a 0 right here for x, meaning there were 0 calls, we'd still get 4.46 arrests. Now, obviously, just like Poisson distributions, just like we did with our quadrant analysis, we can't have, we can round them all up. Remember, we did the rounding, the predicted number, and all that other good stuff too. Okay, and so for each additional call, we increase it by 1.0193. This is just a little different than your 2x plus 7. We know what 2x plus 7 looks like. It's a little harder to conceptualize 1.0193x plus 4.4636. And we have these units here. This x unit is what? This x unit I'm looking here is drug calls versus drug arrests. Now, we can have linear correlations. Okay, we have linear relationships here. So you can see a positive linear relationship, a negative linear relationship, so that y is the dependent variable, x is our independent variable. We can have curved linear relationships, and so we can start to bust out like parabolas, or something like this, y equals 2x squared plus 3, something like that, where we have these parabolic equations right here. So we can fit these to like second order equations, x squared, 2x squared plus 7 or whatever. They get really ugly really quickly with some of these equations, but Excel is okay at those, but ArcGIS Pro, we can run those and it'll give us this right within the confines of a scatter plot. So we'll talk about, and someone remind me after the break for us to go through and look at this, because we're going to look at these case studies as well. So other things we have strong relationships, because remember, we want to create a line that's as close to the points as possible. Okay, this distance here, this y distance, up down distance has been minimized. And so we have a much better line of best fit, and what we call an R squared, goodness of fit, attached to this when the points are closer together as opposed to when they're further apart. And so we're going to talk about a measure called R squared, which addresses that. So you can see this in the positive direction. You can see this in the negative direction. So the positive y and the negative y here. Now, the other thing that we have here, I see something here that goes in a straight line, okay, horizontal line right here. Basically, y equals 2, or y equals 2.734. What is the slope of this line? If it's a horizontal line, what is the slope? 0. Very good. Okay, very good. So what does that mean? Is there a relationship? Is it positive or negative?
It's neither.
None of the above. Exactly. Good. So there is no relationship. And the thing about that is basically as X increases, nothing happens to Y. That's all it is. Because we saw with the EOGs and the attendance, generally as attendance increased, your failure rates decrease, right? It had the outlier there, and we're going to talk about something called the exception fallacy in a couple of weeks, because a lot of times when we use these statistics and we use all this ML and AI and we utilize these algorithms, people make beelines for these exceptions. Like, I know a place that has high, well, the second you say, I know, well, basically you're running into, you're basically proving my point. Okay, but we have no relationships, whether it's tight or whether it's kind of a little bit more scattered. Okay, now the other thing we have is called the residual. So we have regression, which is kind of this just general family of methods that we're talking about. And here we're just talking about linear. We'll get a little bit more kind of robust there because we're just going to let the computer do the work. But we have something called the residual. A residual is this difference between the point and the actual line, okay? Because basically our vitamin D levels for this should be here, but they're really here. And so this distance here is called the residual. So essentially when we create a line of best fit, we're minimizing residuals. And so you can see a point right here, X equals 95. It should be right there at 34, but it's not, it's way up there. And so this difference is called the residual. And essentially, what are these things up here? These things are called outliers. Things that are closer to the line are predicted. Things down here are outliers. We can go and map these in ArcGIS Pro. And it's really neat to go and map these within the confines of ArcGIS Pro because basically it says, hey, these values are much lower than what we say they should be, while these values are much higher than what they're predicted, while the majority of them here are kind of sitting there really close. And so the residual is the observed, which is like 48, minus 34, which is the predicted. So our residual is equal to 14. And we're going to go through and kind of run these in ArcGIS. We're going to run these in Excel here in a little bit. I've got an example there. And then after our break, we're going to play with these a little bit more when we get hands-on. So, oh, wow. Now this is starting to get really ugly really quickly. These are some data here where we have X, Y, predicted residual. I just ran a really simple linear regression where it says that X is the percentage of people who live below the poverty line, and these are heart disease death rate. So maybe, I don't know, maybe it has something to do, maybe poverty or income or, derivations of that, because poverty is based on a couple of factors, which is location, number of people in your household, can be explained by heart disease. And we can make null hypotheses attached to these as well. Okay, because it's going to spit out a p-value for us. Okay, so how much can age-graded heart disease death rates be explained by the percentage of people who live below the poverty line? So are there underlying, morality, other things attached to that? And so when we start to look at these things here, we have our explained and our unexplained variation here. Okay, and I like this slide here. I like this slide here because this summarizes everything with our variability, and we'll kind of look at some real world examples with our variability. But how do we evaluate the explanatory power of a model? Because what have we done thus far with our inferential statistics? We basically, hey, do two groups equal each other? And they should be independent samples. We can do pairwise from one time period to the next, but without using X. How do we predict Y? How much variability exists? And then we have the slope. So we determine the relationship between the independent variable and the dependent variable. Positive slope, Y increases as X increases. Negative slope, Y decreases as X increases. And then no slope, like Gray alluded to before, is just X equals 1, as X increases, nothing happens. Y stays the same.
Also, undefined would be, what is it, y equals 0, I
Yeah.
guess?
X equals something, X equals 5. I think that's undefined because it's delta Y over delta X, right? Yeah, slope is delta Y over delta X. So delta X, if X doesn't change, that's a 0 in your denominator, and we go from there. And hopefully everyone knows what we're talking about, right? Slope is change in Y over change in X for a particular line. That's all it is. In math class, it was like 2X. So you go up 2 and over 1. And this, and the stuff we're doing with real world data, we've got like 1.27. So it gets really, you go up 1.27 and over 1, and so that slope will be consistent, or up, 2 times 1.27 and over 2. So, and that's a really good question, Ray. I appreciate that. So our residuals, okay, measuring the variability is our distance between the true values and our predicted values. Okay, so we've got these residuals right here. Now we have something here called R squared, and we're going to talk about what that means because ArcGIS Pro gives us R squares. So ArcGIS Pro is really nice. We don't even have to go and run anything just yet. And we can run scatter plots, and we can run bins and all those other good things that we've already done before that can give us some really easy R squareds without getting too much in the weeds. We have R squareds. Values close to 1 mean that X can explain variability and Y with more confidence. Okay, because thus far we've been talking about p-values. Lower, we're looking for, maybe we don't want low p-values. We just know there's something statistical happening there. Now, the other thing, and this is where people start getting into the weeds a lot more, is residual analysis. So, and we'll start busting out some big words like multicollinearity and heteroscedasticity in a couple of weeks when we talk about some caveats to this. But a lot of times when we map residuals need to be consistent across the x-axis. So these residuals shouldn't look like this. They shouldn't look like this. So we know that they're not independent variables, because a lot of times, if I were to make a map of, say, let me map on x-axis percent majority versus percent minority population. Well, they're the exact opposites of each other, so they're going to be they're going to be in a straight line. We all should know that, right? And so when we start throwing these things into multilinear models, multivariate models, those things start to basically cancel each other out. So when we start to do residual analysis, and we'll look at Excel today, that gives us, it is able to map the residuals. Now I'm not as good a statistician as I probably should be, but I do go through and make sure my residuals look good when I can. Other things, examples of approximate R squares. R squared is equal to 1 when it's right on the line. Doesn't matter if it's positive slope or negative slope, okay? Because whenever we square a number, if we raise it, because we can have an R value, and then we square that value, basically, which means it's always going to be positive. We can't square a number and have a negative number, because negative times negatives equal positives. All right, so we got examples of R squareds. These are weaker linear relationships between X and Y. They explain some, but not all of the variation, because guess what? I'm going to circle back. I'm going to circle back to this one here. And so this is my map here. This was extracted using GIS techniques. Now I'm talking about Excel. And to me, when I do my statistical analysis, I'm doing something really simple. I could just bring it in. Let me just bring it into ArcGIS Pro. I haven't done it with the tabular analysis because a lot of times I'm running these things on zip codes or block groups, which have spatiality attached to them. But let's see what we got here. Now I mapped this. There it is. And I've mapped per capita income, because basically what we do here, and I'll go back to this one in a second, is we have these data points right here. Now, instead of having 67 data points right here, I've got 2, 4, 8 data points right here. And the equation for my line that it spits out for me is my predicted y equals 2.9x plus 2.7. Fill in the rest of the table using the techniques we discussed in class. Now, first question is, what is the y-intercept? Intercept is 2.27. Or 2.7, I'm sorry. Is this a positive or negative correlation? It's positive. Why? Because the slope is positive. Now, what I've done here in Excel, and hopefully I still have that Excel file, this is a correlation table. And I'm kind of just looking at this here. But what I did right here is I put in my X's and my Y's, and then I put in the little equation here, which is 2.9 2.9x plus 2.7. So I've got my X and my Y, and basically these are these points right here. Okay, so I have some type of observation, and this is where they lie right here, because in theory they should go up, but I've got a case here where they kind of stay the same here, and another one that kind of increases dramatically right here. And so what I did was I just plugged in the points right here. All I did was cut and paste, and then I used the equation from my line of best fit, which said 2.9x, x, remember, is A2, plus 2.7, and I just dragged it down. And then my residual is equal to my observed minus my predicted. So that 1,5, it really should have been 1,5.6. That 2,10 really should have been 2,8.5. 3,11 should have been 3,11.4. So this is what we call our residuals right here. The difference is if I were to go and graph these, okay, if I were to go and graph these, I'll probably embarrass myself and try graphing these now, but yeah, let's do it. I'm in the mood to embarrass myself. That's fine. Okay, so I can run a nice little scatter plot right here. All right, look what I got. Okay, it's kind of treating me well right here. We'll kind of ignore these for now, but these orange ones are the line of best fit. These blue dots are my observed values. And then these greens are basically my residuals. Now, in theory, when I highlight my residuals, they average up to be what? A really, really, really small number, right? 6.6 E negative 16, what is that equal to? Really small. The sum is very, 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 very small, okay? You know, because I kind of plugged these in and it looks like I probably rounded these a little bit. But look how small. These averages, these should average up. These residuals should add up and average 0. And look what, looks like they did. And so when we talk about looking at relationships between X and Y, that were X and Y predicted, these residuals should fluctuate. They should fluctuate above and below the mean and add up to 0. So you can kind of see, you know, the relationship that we have here. So I've got a kind of a simple little Excel that I ran right here. Now let's do some practical applications with this. Now these are some of the things that we're going back to with the bear sightings. So black bear in December, they typically have a bear hunt because there's about 2,500 to 3,000 black bear that reside in New Jersey. So these yearly bear hunts help keep it stabilized. Most of them occur in Northwest New Jersey, but many, all counties in New Jersey have seen them, even though 30 years ago that wasn't the case. And so once again, we did this. The reason why we did this study here, and you can see the spread of the bear population, where that black bear, where that in 1995, they went about this far. This is kind of when I left. And then by now you can see they're in all these different counties. And we created the quadrants, and we'll talk about the quadrants because we've done previous bear studies in Colorado, British Columbia, other things right here. But these were provided as addresses between 2010, 2012. How do you get the data? Most of the work was just getting the data. And so we went and what did we do? We went and created these quadrants right here. Why did we create quadrants? Why did we create quadrants? Let's sit here and twiddle my thumbs for a second. Why do I create why do I create these squares? Let me look at this thing here.
Well, one reason is like because you nice equally sized like
Exactly.
intervals to work with.
Exactly, nice, equally sized. So I don't even have to calculate density with those because when we look at these are townships and boroughs which have different sizes. So we see these things here that happen to be white that didn't have a siding. That's probably because they're so small they didn't have a bear siding, where these other areas next to it are so big, chances are better of it having a bear siding within it. So, and also within these, I start to look at what do you think impacts bear sightings? This is kind of off the cuff question here, but what types of areas would have more bear sightings than others? Like, what are things that attract bears? Does anyone even know? What would have been your bear interactions?
Food, maybe.
Food, definitely. Food and water, exactly. And so what I started to do, exactly. And then people, these are the big problems that we run into. But some of the things that we calculated here were percent water. Is it close to a water source? And these are easily calculated by squares. Percent water in wetland, percent developed land. Okay, I got these from something called NLCD. And so these NLCD is National Land Cover Data Set. And you'll be working with those if you take raster GIS next semester. Pixel variety. Pixel variety is a metric that I really like because it has the number of different land cover pixels in an area. Because if I'm a bear and I just walk from forest to forest to forest to forest to forest, what are the chances of me running into a person? Really small. If I'm a bear and I have to go from forest to urban to forest to urban to urban to forest to water, what are the chances of me running into a person? A lot better. But these are all raster data. Total number of highway miles, average distance to roadways, average distance to landfills. I had a couple things here like population density that I calculated for the square. It got a little ugly. Distance to rivers, distance to lakes, average elevation, slope. Do bears like to walk on even areas or walk up mountains? I don't know. Distance to open space. And so I started to calculate things like percent forest. This was percent forest by square, which is really easy to calculate. This is pixel variety. So you can see the number of different types of pixels. These yellow ones are probably just all forest or all lake. And then I started to run some nice little regression models right here. And I did this in a programming language called R, which is distance to lakes, bear density. What is my bear density? And so if it gets really far, if they're really close, I have really high density. And so this isn't linear, but it makes a nice little curve like this. So it makes a nice curve. And so we look at T values, which are attached to P values. And so we can look at these curves like this, because when we look at curves, we got like parabolas right here, right? We can fit equations to parabolas, because basically that's all we want to do. That's really what AI and ML and clustering really does. We just fit it to parabolas that get, linear. I like. This gets uglier. This gets much, much uglier, and then we get, raising things to powers, which gets uglier. And then we get into all of our sines, cosines family, and then we get into some of these hyperbolic curves. And to me, I'm starting to get into some of these like logistic curves where we're looking at Booleans and fuzzy logic right here. So yeah, this is a yes and a no or whatever here. Now, how do we interpret these things here? Because when we go back to what we did previously was we have our supermarket availability, convenience store availability. And we're going to kind of look over here where that that graph that I showed before where I looked at per capita income in dollars versus convenience store availability, it's got an R squared of 0.3153. Okay, and our P score is really, really, really small, like 0.00001, meaning if I were to throw those 76 points up onto that chart, they would not appear like that. And you can see with convenience stores accessibility as opposed to supermarket store accessibility, there's a whole lot of positive correlations. I also put if they're positive or negative correlations here, a whole lot of positive, both positive and negative correlations here attached to these. Okay, like per capita income basically means as per income increases, availability decreases, or vice versa. But you can see this here. But so now what we're looking at here is about 32% of the variation in distance convenience stores can be explained by income. Well, that's pretty deep. When we look at, how convenience stores are placed, we can explain 32% of it, almost 32% of it, just via per capita income in dollars. That's it. Okay, the rest is everything, but because what determines the placement of a convenience store or distance convenience? Tons of things. Zoning. So you can definitely see relationships between here. Do you think it's intentional that convenience stores are in low-income areas? This says it isn't. I don't think it is either. Now,
I don't think so.
What?
Sorry.
What'd you say?
I was gonna say I don't think it is either.
I don't think it is either. I definitely don't think it is. Okay. Some of them might be zoning. Some of them might be, zoning meaning that these are in high density areas, which is where a lot of your high density housing is. So convenience stores along these major thoroughfares, where that higher income areas are set off back away from the, high traffic roads, which have a lot of your which have your convenience stores and everything. Okay. So we also have something here called multiple regression. This gets ugly very quickly. So you can just see if we have two variables that try to explain one. So now we have a plane right here. So this is just, and it gets really ugly really quickly. So our Y value is based on multiple coefficients plus some random error. So if you want to predict, residential burglary from income, vandalism, and households, we start to get into this, which gets really ugly really quick. We're going to look at a couple here. How well do different variables explain age-graded disease death rates at the zip code level? Okay. So a lot of times we see these little stars. Yes, little stars are good. Little stars are good here. Okay, I see things here, highest adjusted R squareds here. So what we're going to try to do today is just interpret some of these, because when we run these, it gives me R squared of 0.24, 0.27, 0.13. I think I ran this last one here, 0.27, where, all right, it's negative percent minorities, so poverty, average home value. So we got to figure out how to interpret these, and we're going to run these ourselves later. I'll run these ourselves because we get these tables that look something like this. And this is what we got here, or that, what do we care about? Not T values, but we got our probability values. Me, I like to look at the little stars right there. Star, star, star. I see a star, I look for low P values. And so this is attached to average home value. In poverty, you can see one's negative, one's positive. So we do know that as home values increase, poverty is going to decrease. So we can see that these are opposite of each other. So one's going to increase while the other decreases here. Percentage people over the age of 55. You notice here, this per capita income is 0.08, but it's not starred. And so this significance level that we're looking at here is that it's less than 0.05. So you see a 0.005, 0.004. I can see a 0.069. We'll kind of go through and figure out what those mean. And then I look at these robust probabilities a little bit more here, and I can see the stars attached to those with the diversity index. Now, this is what Dr. McGinn and I did for the by-mail voting rates. Okay, well, this is what your paper is going to be on too. So maybe just go back to this recording here when you start working on it. But what we tried to do is we used all of these factors. We threw, and I just did this in ArcGIS Pro, is I threw all of these factors in here to figure out all the factors that explain by-mail voting rates. By-mail voting rates. So anything with a little star, and this is the y-intercept because I've got the coefficient. So as you can imagine, this is multiple regression. So as you can imagine, the equation for this is really, really big because we're looking at about 10 different variables. So we've got the coefficient, we have our t-statistic, and we have our probability. So what this says here, population density has a star. This number is positive. And so as population increases, by-mail voting increases. Does that make sense? I hope so. So it's got a positive rate there. Okay, positive. Income. As income increases, by-mail voting increases. Okay, so higher income areas have higher by-mail rates. And we could also justify this with clustering as well. Now, just for the most part, clustering is just going to be spatial in nature. You know, when we look at, all right, this is red and this is red, because when we map density and median household income and poverty rates and percent minority and COVID rates and all these other things, what's happening there? Where they're making separate maps here. And once we start making separate maps, our brains get overwhelmed. You know, we're looking at 10 different maps with a by-mail map. So I think this chart here puts it a little bit more into perspective here. Now let's look at this one here. Poverty rates. It's got a probability of 0.45. We know that's not statistically significant. So poverty rate has no impact, statistical impact on by-mail voting rates. So rich, poor, doesn't matter. What else do we have? Percent minority. Now this is negative. And so as the percent minority increases, what happens to by-mail? Decreases. Okay, so this is negative right here. So we can see the negative on the percent minority for this particular coefficient, and it's statistically significant. So basically, high minority areas had less by-mail voting rates, which contributed to this model here. Right? This is just a big, gigantic of the equation that we don't want to kind of conjure out. And the last thing that was significant was average vehicles per household. That's also negative. So as people had more vehicles, by-mail decreased. Does that make sense? Yes, so, right? Kind of makes sense. People with less cars are going to send in their mails, they're sending their ballots by mail. Okay, cool. The one thing that I was scared about was by mail in 2016. I was kind of scared that this was going to be significant and this whole paper was going to blow up after we had spent time writing it, because someone said, hey, you better go back and revisit, because typically when you submit these, work on these, you get 2 or 3 reviews. Said, hey, you better map the by mail rates for 2016 to make sure they're not significant. So the by mail, they don't have a little dot right there. So that means they are not significant. Okay, meaning that 2020 by mail voting rates were not impacted by 2016 by mail rates. Now, what we're going to do here, we'll take about a 10-minute break. We'll meet back here at 6:21. Is we're going to open up case study. study number 5. So I've got the map here ready to go. So we're going to open up case study number 5. I'll go through the process here of opening up with you because I know some people still have trouble where to get it and how to open it and all that other good stuff. But those of you who are, let's get this open up. And what we're going to do here is we're going to play with some of the things here when we open up the attribute table, looking at relationship between spending on fast food and percent minority or diversity index, or just some of these general things right here. So we'll take about 10 minutes. I'll see you back here at 6:21. Got a couple minutes here. Okay, here we go. Let me close my door. Okay, so what we're going to do is we're going to go through some variations of correlation and some OLS multiple regression here. So we're going to open up this exercise. We're going to start this from scratch. So we're going to go to Canvas. Okay, I will add Canvas on over here. Canvas. Okay, here we are. Topics, modules, and I believe we're in week 10, and we'll talk about all the kind of deliverables that we'll have for next week, which is going to be pretty minor. All right, so here we've got predictive analysis. I've got the topics we discussed. I've got the PowerPoint presentation that I just gave. I have a recording of the PowerPoint presentation. I've got reading number 4 and Esri assignment number 3. These will be new next week. Make sure someone reminds me to go back to those. But the reading is going to be on the correlation that we did with the by mail voting. And just read it. It's a short read. It's 3,000 words. And so that's probably one of my favorite papers. One is because it's short, because it's really hard to write, be intentional in 3,000 words. 2, it's called the Professional Geographer, which is the kind of applied journal for the Association of American Geographers, which is the largest geography association in the world. And I like the paper. It's easy to cross-pollinates with political science, and we got that out like real quick. Case study number 5, which we'll open up. I have some textbook material on the book from Mitchell and statistics, least squares analysis. This goes and explains some of the least squares. And then I have a couple of videos. One is using ArcGIS Pro to run simple regression. One is running some very simple linear regression in Excel. And so if we have time here, we're going to go through all of these. We're going to go through all these. So we're going to open up case study number 5. Okay, so we've got case study. It's a zip file. So I'm going to click the little zip file, and however your browser downloads things, that's what you're going to go to. So you can see right here in my downloads, you can see I've already opened up before. So I have case study 5.zip. I'm going to click on this. Here it is. Make sure you click extract. Okay, because when I click on this thing, you can see it's got the case study 5, it's got the GDB. This is basically the geodatabase that contains all the points, lines, polygons, attributes, everything as well. But make sure you click extract. Okay, click extract. Okay, and I go over here. Okay, I've been on some people's computers, and I'm really impressed. When I say, hey, working with them hands-on, they have folders dedicated explicitly for this class. So I'm really impressed. I don't want to point anyone out, but there's a couple of people that say, hey, go to my documents, my Geostats class. So we have that. So that's really good for data management, but I'm not going to do that. So I'm going to click extract. I'm just going to store it in my downloads, and I'll show you why. Because now this is going to look a lot the same, but now this doesn't have a little extract right there. So now if I were to go to download, you would see this is sitting there for me. So I'm going to go to my case study 5. I'm going to double click on it, and I'm going to double click on the case study 5, and up is going to, I'm going to shut this one down and close that project. And I'm just going to open up a brand new project right here. So you notice in this class, we've been kind of circling on some different themes here. A lot of this is health related. We've done some other things with deer vehicle collisions. We did the cancer rates at the state level, working with raw cancer data, but we've got zip codes. And what we're mapped here is the age graded death rate here. And so remember, we went and mapped the raw death rates here for certain diabetes and I think it was heart disease. It's been a while since I've done this. I probably need to go and kind of redo these. But this is age graded death rates, and we can run cluster analysis on these. And I think we did this a little bit last week, where obviously you can see it's higher in the southeast portion, lower in the northern portion right here. So these are age graded. So imagining every zip code here has the same exact average age. Okay, that's what age grading means. We weight it by age. All it is just a weighted equation. All it is a weighted average. That's all it is. Based on the age-specific death rates, which you have to go through and extract yourself. So those things get really difficult. And in a couple of weeks, we'll talk about small number problems. And I know some people answered some really good questions about small number problems previously. So we've got this, we right mouse click and we can click on open attribute table. So when we look at this open attribute table, we've got 82 zip codes sitting here. These are just some of the attributes that I've let people have access to, but I have POP 2013, median age, the age graded death rate, the number of healthy food sources, the number of unhealthy food sources. We have something called the RFEI, Retail Food Environment Index, which is basically 19 divided by 5. So this is the ratio of unhealthy to healthy. And then we have something called the Modified Food Retail Environment Index. You all didn't think you'd be learning about food desert stuff here, but these are the percentages of stores that are healthy. So basically this is 5 divided by 24. And so these percentages go from 0 to 100. These can go to whatever. If you have 101 or whatever, typically, you can see those, 3, 4, 5s right there. All right, other things I got if it's urban or rural. So if you kind of wanted to run some urban rural, we do have some papers out there. What constitutes urban? What constitutes rural? So I don't want to go down that. I don't want to go down that. Median household income, spending on fast food, percent minority diversity index. That's kind of a number based on the percentage of different races. There are about 6 or 8 different races that the census defines. Spending on fruits and vegetables, spending on fast food, spending on medical bills, percentage of rentals, percentage of people who live in rental homes, spending on drugs and vitamins, average number of vehicles, people who live below the poverty line, percentage of people who live below the poverty line, percentage of people who live below 150% of the poverty line. So if the poverty line just happens to be $40,000, this is people who live under $60,000 based on your family size or household size and location. Average home value, per capita income. So I got a lot of variables here. Now the first couple things we're gonna look at here is I'm just gonna right mouse click, and some of the things I can do is I can create nice charts. I like my bar chart, or I like my histograms. I like my scatter plots. You can go through and calculate all these other things here with data visualization. I'm a big scatter plot guy. I'm a big histogram guy, just because I want to look at that nice normal distribution as well. Box plots I like, but so I want to map scatter plot right here. Right? I just want to create a scatter plot. And I'm going to click on the properties. And so we have our x-axis and our y-axis. And we're going to show some really neat things right here. Okay. So some really neat things. And just, I want to explain one using the other. I want to say that, I don't know, this is pretty simple one. Poverty can be explained by per capita income. This is just really simple here, right? Okay. We can see the relationship here between poverty and income. Okay. These kind of go these go hand in hand. There's other extenuating factors in there, like where you live. But you can see when I create this, look what ArcGIS Pro does for me. R squared equals 50.54. And if I wanted to, look what I have right here. Show trend line, y equals 46.1 plus negative 0.0012x. So we've got our y equals mx plus b, because when we look at these units here, these units are in dollars and in percentages. So I really like what ArcGIS Pro has started to do. So what we can start to do is, hey, instead of my X here, let's see if there's a relationship between, well, we were talking about age-graded rates, our age-graded cancer mortality, death rates, and per capita income. Is there a relationship with these here? Now I get an R squared, and I'm looking right here, R squared is equal to 0.04 or 0.0356, really, really small. Now we're gonna have to run these through Excel to see if they're actually statistically significant. But this is the trend. Now this is negative. So basically it means that as income increases, the heart disease death rate decreases. Probably makes sense, right? So we can kind of play with these here as well. Remember, and the other neat thing that I can look at here is we can look for outliers. Okay? We can start to look for outliers on some of these things here. Okay, you can see, over here, these have low income, but what? They have below average death rates. So, hey, what's going on here in these zip codes, which are lower income, but have low death rates? Okay, what about this over here, which is higher income, but above what it's predicted? Okay, above what it's predicted right here. So we can go through and play with many of kind of the machinations with this here, Can we see if it's related to spending on fruits and vegetables, spending on drugs and vitamins? Can we see if it's related to, say, median household income, home value, or whatever here? 0.15, it's a little bit stronger there. So we can see which one of these are strongest. MRFEI, R squared is equal to 0. Okay, good. Okay, we got, now this X, it says 1.96, but when we're working with the Y-intercept of 1023, you can start to see, these units get, this looks like a horizontal line. Well, people are sitting there telling me it's, 1.196, 1.96, but when we look at the units here, are you going to notice that 1.96 across here? Of course you're not. Okay, definitely not. So we've got these here that we can play with. The other thing is, okay, and we're going to look at a couple of different things here, but the next thing that we can do is that we can pop all these into Excel and get some more robust calculations with our linear regression. And then we're going to come back to ArcGIS Pro and do our multiple regression. So now what we can do is I can clear, switch. What can I do? I can put every single thing here into Excel. Okay, so I got my correlation chart right here. What I'm going to do is just put every single thing here into Excel. And now I want to see if there's a relationship between how strong of a relationship there is, because it gave me an R squared before, but it didn't tell me the p-value. Because I want to find some examples where there's high, no p-values, high p-values, some other things related to that. So our age-graded death rate versus maybe percent minority, maybe there's a relationship between these. Now, when I look at these, what are some weird things that I see? This is kind of some of our data preparation here. Fort Bragg is 0. You know what I'm going to do right now? I'm going to go and delete it. Why do I want to delete it? Who can I pick on? Who's paying?
I mean, you don't have good data for it. You have no
I don't
data
have
for
the
it.
data for it. Yes. Do you think it's really 0 there where everything else is 1,700? Probably not. So we're dealing with some small number issues there. Okay, dealing with some small number issues there. We just might not have had one. I don't want to go and start, averaging 0 here and bring everything down and really mess up my model. Okay, and I did throw it into that other model before, but who's counting here? Okay, so let's just maybe see if there's a relationship between our graded heart disease death rates and percent minority, and then we'll bring them into this other model because I'll probably go back and delete that later. So what we're going to do here is we're going to go data and data analysis. Now, where have we been sitting here thus far? We've been sitting here. We got ANOVAs up here. Single factor. I just run the single factors. We got correlation, covariance, descriptive statistics. We know what those are. Now, all these tests are slightly different. We got our two-tailed t-test assuming equal variances. For the most part, that's what we should do. So we're going to click on regression. I'm gonna click on regression. And what am I going to look for? I got an input range, output range, residuals. I got lots of plots right here. I can put in a new workbook, output sheet. Now, the first thing I want to do is what's my why? What am I trying to explain? All right. Age graded mortality rates. Okay. And I'm actually going to go because I had already run this just to make sure I wasn't messing up. So our age graded mortality rates. Next, X. What explains this? Because this software, Excel, doesn't have multiple regression. That's what we're going to go back to ArcGIS Pro and do. Okay. And what we're going to do here is we're going to look at percent minority. We're just going to grab those values right here. Remember, we got rid of one of those zero values, so it might be a little stronger this time. Okay, I want to look at the residuals, standardized residual plots, line fit plots. Okay, because we can cut and paste these and cater these a little bit to what we want. Labels, confidence levels. Okay, let's click OK and see what it gives us. Line plot, residual plot. Okay. So this is our residuals right here. Okay, we're getting ahead of ourselves here because what are we looking at here? We are looking at our coefficient is positive. Okay, first of all, what's that mean? It means as one goes up, the other goes up. Okay, line. Okay, this is our predicted. Okay, here. So looks like these are our values. This is our predicted right here. Okay, so this is percent minority, this is our rates. And so you can see here a little bit, not a little bit, but you can see here as percent minority increases, so does our age-graded death rates, because what tells me that? That coefficient. Now, what's my p-value tell me? 0.13, is that significant, yes or no? No, it's not significant. It is not. It's close to being significant, but it's not. It is definitely not. Okay. Now let's try to find something where it is going to be significant. This was close. Okay, this was close. Now when we map our residuals, if someone were to go through and map these, because these days, when you start writing papers, what else do you need to do these days? Who took data science class? Anyone take data science with me? I'm going to pick on someone that took it. Hi, Andy. Hi, Michael. What do we got to do? Whenever you publish a paper, usually what do you have to do? I'm just putting him on the spot.
Yes. Hello?
I'm putting Andy on the spot a little bit just because he took my data science class last semester. After we did some of the programming, we did open science. What's open science mean?
Open science, that's data available to the public. That's when you do a research, you need to make your data accessible to everyone.
Exactly, right answer. Excellent. So a lot of times we can create open science, create a DOI, digital object identifier, with all these Excel spreadsheets and all of these here. So if someone asks, hey, my data is sitting right here, that you can go and download and look at exactly what I did right here. And that's really important. We spend a week or two doing that. In data science, where that you create some data, you publish it so that at the end it says, if you want to download my stuff, here it is. And so it creates unique DOIs, digital object identifiers, basically URLs, so that you can go, someone else can go and download it and look at this exact data that you are looking at. I think that's to me, it's important. It's groundbreaking. I don't want to belabor the point too much, but they're not sitting behind firewalls or any of that other kind of garbage that we deal with these days. Okay, so what we have here, this p-value tells us it's not significant. Not significant. Do I have a sheet 4? What's this? Oh, this is our original data here. Okay, so we can see there is a relationship. It's a relatively strong relationship, but it's strong, not strong enough for us to say it's significant. Okay, all right, let's look at another one. What are some other things that might impact it? Let's look at age-graded mortality rates versus, I don't know, let's think of something. Let's just look at income. No, that's an easy one. That's a really easy one. So regression. Okay, so I got H2. Okay, so we got the columns. I'll keep everything else right here. So H2 is my column here, my input range. This time I'm going to go over to median household income. So my null hypothesis, if we want to use that term, is that there is a relationship, or there's a relationship between median household income and age-graded cancer mortality rates, or more general. And these are some of the things that maybe you want to do for your position paper is I want to look at the factors that impact by mail voting rates, age-graded cancer mortality rates. And you run each of these individual tests and say, all right, P of this, P of this, P of this, P of this, P of this. You run them individually. And then maybe we could throw those into a multiple regression model that further supports those. Because when you start throwing in multiple regression, which we'll see in a little bit, things get a little wacky a little quickly, especially if we have what we call multicollinearity. Multicollinearity, which means two variables are related to each other and they're basically canceling each other out. Okay, so enough of the big words here. I'm going to just click OK. So we got our line fit here. Okay, income. What do we see here? All right, it's negative. So basically, as income increases, death rates decrease, but not quite statistically significant. Not quite close, but not quite. Okay.
Okay, can I ask a question?
Yes.
Does that, okay, so if that's not enough to say then that higher cancer rates are caused from, I'm just being a devil's advocate here. Can you draw that conclusion or not?
No.
Okay.
No. Now, what I'm doing here is just running these pairwise so that you can run all of these against each of the individual variables. And then what we're going to do is we're going to throw them into a multiple regression model where they're going to be playing off of each other to create an equation. But yeah, but I might need to go clean up the data a little bit or something like that. But, it's strong. It's a strong relationship. It's just not strong enough for us to say statistically significant. We'll run one here that I definitely know will have a relationship because I don't want to disappoint anyone. Let's see if there's a relationship between just poverty and per capita income. We know they're largely related. We saw that R squared equal to like 0.54, but I just want to show you something where we're definitely going to have a distinct relationship. So we're going to look at to see if poverty, so that's going to be my Y, can be explained by per capita income. And we know it probably will be. Why? Because poverty levels are determined by a few different factors: location, family size, and income, and maybe one or two other things. But the large driver of that is going to be income. And then per capita income. Okay, let's run this. Now, if you're responsible, like I'm not, basically what you should be doing also is like right mouse click, rename, poverty versus, income results. You know what I mean? Now, what do we have here? This is what ArcGIS Pro told me. We got an adjusted R squared of 0.54. So that means more than half of poverty can be explained by income. Okay, and then what do we have here? We have a negative correlation. So basically, as income increases, poverty rates decrease. Okay, that makes sense. And then we got a p-value of 4.54 e negative 15, which is 0.14 zeros, and then those numbers right there. So that is very, very, very significant. So, but when we look at this line plot, all these mean is that we're looking at these blue points right here, which we mapped. The chances of me throwing up 80 observations and it looking like this are really, 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 really small. Okay, with this, with these points right here, okay, we're looking at this one here, point, the chances of me throwing points up here that will have this pattern are about 11%, but 11% is above our threshold to say that it's statistically significant. Okay, so there's still a chance, 1 in 10 chance. I can throw up 80 points, it'll highlight that pattern that looks like that. It kind of like your nearest neighbor analysis, but not spatial. Okay, so we've got some really good Excel work that we've done here. And I have a really good video that explains all these things here because our T is basically, it aligns with our Z-score, which is converted to a p-value. We've got our confidence intervals. I don't want to say I don't care too much about those, but what I worry about most is coefficient to look at the positive or negative relationship. I got a p-value right here, and you got your intercept right here. So right here's your slope, right here's your y-intercept. Okay, I don't care. I don't want to say don't care isn't the right word, but I'm not as worried about the actual equation itself, more about the relationship with the coefficients and the p-values for me to concretely and authoritatively say there was a relationship between the two. Okay. All right, what else do we have here? Let me look at my PowerPoint. All right, so we're going to use OLS right here. So now we're going to go back to our map right here. And we're going to open up some tools right here. We're going to just open up what we call OLS. So now we're going to go to Analysis, Tools, and then we got our favorites right here. But I'm going to go to my toolboxes just because I like taking a tour through my tools and look at all the things that I don't know. I don't really, most things I don't really care to know. We got our spatial statistics. And then even within these, we've got geographic distributions, modeling spatial relationships. We've got these modeling spatial relationships right here. Even with these, and next week we're going to talk about GWR. There's always just brand new things coming. Generalized linear regression. These are some things we've talked about. This will fit things in planes. But what we're going to do here, I'm just looking at this tool real quick. Maybe not so quick. Okay, we won't. We're going to run what we call ordinary least squares. And you can look at the general linear regression. That just might be one variable versus another variable, but that we did right here. As you notice with the new iterations of ArcGIS Pro, they're always adding more and more new tools. So that's really, that's pretty neat. All right, so we got OLS. The generalized tool provides enhanced functionality. Okay, cool. All right, we'll look at that. Question mark here. This talks about OLS right here. Predicted. So if you really want to, or yourself, put yourself to sleep, you can do that. All right, so our input feature class is going to be what? Zip codes. All right, it needs a unique ID field. Okay, so you need an ID right there. I don't know why it does. There's probably something within its, so it's got an ID. And if I remember right, I went and created an ID for this. And I'm just gonna drag this over here because I think when I was making the exercise, it needed an ID. And so what I did was I created a number called ID and I just copied it from this object ID. So I made it a number, I copied it because it needed an ID. Okay, now my output feature class is going to be this, my dependent variable. What are we trying to explain? We try to explain by mail voting rates for 2020. That was my whole goal before. What are the factors that explain those? Here is the age-graded death rates, these heart disease-related death rates here. What are the factors that we want to explain? Okay, well, we don't want to do age-graded death rates because it's just going to be a one-to-one relationship. So we got median age. Let's look at median household income. Spending on fast food, spending on fruits and vegetables. Percent rentals. We'll say poverty rates. We'll just pick a couple of these things right here. Now, some of these are related to each other, so I just want to kind of run these and we'll look at maybe diversity and percent minority here. Because remember, when we go back, what those results gave us before. Now, when I go through and run my OLS, I'm probably going to be a little bit more intentional about this. And while I'm thinking of it here, oops. I was going to click on that. Generalized. Okay. All right, dependent variable. I was going to click on the tool and go back. Age graded rates, median age, because age should matter, right? MRVI, access to food, percent minority diversity index, spending on fruits and vegetables, spending on medical bills. We'll just click on a couple of these here. All right. Output file report. I'm just going to save it right here in case study number 5. Okay. Save that there. Well, let's just run this thing. Let's see what it gives us. And this is going to look a lot like our clustering. So to be honest with you, it's going to look a little. With the bins and all these other extraneous things that we don't necessarily need. All right, now, what do we got here? We've got a map. Okay, we got blues, we got reds. Okay, basically, now if I were to right mouse click and open up this thing, I go here, the age graded rates here, estimated, residual, standard. So this has got the approximate value, the predicted value. This is the age graded rate, what it should be, what it is, versus what it should be based on this model. That's what it's predicted. And then the difference is the residual. So you can see this one right here. It doesn't have that much of a difference. Now, if I were to right mouse click and sort ascending, what do we have here? Uh-oh, I messed up. We won't talk about that. Now, you see here, this has got the worst residual. Why? Because it's got a rate of 0. But this one right here, the estimated was 1010, but it was really 385. So these ones in blue are basically values that should be higher than what they really are. These values in red down here are values that should be lower than what they are. So you can see some of these age graded rates, which are really high. These could be due for a lot of reasons, anomalies or whatever in the data here. Now, when I go back to this here, Okay, and this is also going to be stored in a report. Now, what's it say here? Use spatial autocorrelation Moran's-I to ensure residuals are not spatially correlated. Great idea. Thank you. So what do we have here? Probability. Multiple R squared, 0.1111. Oh, it's a lot of garbage right here. Okay, this isn't very strong. What does it say here? An asterisk indicates statistically significant P less than 0.01. So probability, robust probability right here. What do we see here? Do we see anything less than 0.01? No. So I've thrown this into a model and it's gotten really not very good, to be honest with you. I've got the y-intercept, median age. Let's run another one right here with a lot less things because I think these things are canceling each other out. So let's just see if there's maybe a relationship between spreading on fruits and vegetables, percent minority, poverty, median household income. Let's just run it on 4 of these here. Let's run it again with 4 of them. Let's see what we got here. Multiple R squared of 0.06. Age graded rates, robust probability, no stars, no stars, no stars, no stars, nothing. What's that tell you? Look at the distribution of these things right here. Standard residuals. What predicts age graded death rates? Not a lot. Not a lot. Maybe income a little bit, but not very much. Not very much here. So I really like these, tools here. Now, it not being statistically significant, that's an answer. I think that's probably going to be a better answer than what we're looking at because it basically reinforces what we're looking at. Hey, is there a relationship between the death rates and the race? Excel told me no. This tells me no as well. So they both tell me no. So to me, there's probably, I don't want to use the word randomness, but there's probably a lot of other factors that I don't have here, sitting here with percent minority, RFEI, retail food environment index, age graded death rates, percent rentals that are way above and beyond those. I really like those. Let me just run that analysis tool real quick, the regression one, because it kind of gave me a little warning there. So I kind of wanted to check that out. All right, let's see this one here. So this says OLS, this says generalized linear regression. Okay, let's see. Let's just for the heck of it, let's just see what this thing is. Generalized linear regression. All right, performs general to. Okay, binary, logistic, Poisson. We know our friend Poisson. Count, continuous binary. Okay. Oh, wow. Look at this. You could get really good really quickly at all of these things here. Just going to run this. Continuous data logistic, which basically means 1 or 0. or a count. So we got our Poisson distributions right here. So Gaussian is continuous, logistic is 1 or 0. Is based on these values, is it a yes or is it a no? There's some really neat things that you can do here. Really neat things that you can do here, or is it going to be count like we've looked at before? Let's just look at the spending on fast food, percent minority, poverty rates, spending on drugs and vitamins, and spending on medical bills. Just for the heck of it, let's just run it because I want to go through the exercise here. I just want to see this output. I haven't used this tool because this looks like it uses nonlinear equations as well. So just for the heck of it, let's see what we have here. All right, here we got some probabilities on using GLR. Death rates are related to spending on fast food, spending on medical bills, negative, and spending on drugs and vitamins. All right, so when we run the generalized linear regression, let's see. People who spend more on fast food have higher death rates because you can see it's positive. People who spend more on medical bills have lower death rates because this is negative. Poverty has nothing to do with this particular model. And then spending on drugs and vitamins is positive. You spend more, you have higher death rates. Maybe. And then minority and poverty, they have nothing to do with each other. They have nothing to do with this particular model here. Okay. But our R squared right here, look what our R squared right here is. It's like 0.11. We're looking at 0.06 here. These are really, really small. So most of your variability, it can't be explained with spending on fast food, spending on fast food, percent minority, spending on medical bills, spending on drugs and vitamins, or poverty. There's still 94% of the explainability out there that, to be honest with you, a lot of it can't be encapsulated. Now we work with physical phenomena, but we're working with social phenomena. So this is going to be a little bit different when we work with data because there's so many qualitative factors that can't be encapsulated, not only a person by person basis, but with the encapsulated on a map. Okay. But once again, you can see the standard deviations right there, where they're high, where they're low. You can see I probably messed up my model a little bit because I included that Fort Bragg one, but I can just easily go in there, click on edit, delete that, rerun it. It might give me slightly different results. Okay, hopefully. Okay, any questions for me here? I'm almost done. All right, so what we have here is reading 4 and Esri assignment number 3. So I've got all the videos up here. I've got all the book materials. So I've got reading number 4. I have this due in a week from today at 5 at the beginning. Remember, undergraduate students, because a few of you are joining us here. Undergraduate students, you only need to do 2 of these. If you do 3 or 4 of them, those extra 2 will count as extra credit. Okay. Graduate students, I'm not a big believer in graduate student extra credits, so you have to do all of them. So we've got this here. We can kind of read it here. You can see what it looks like. Try to explain. We used OLS right here. I bet you we'd probably have the same general results if we used same general results if we did the other values. But you can see right here, this is the question that they asked me here. But make sure you read these. You look at these here, because when we look at this paper here had this, but then I went, did I add another table right here? Oh no, I got another really, really cool, okay, this cool paper here, this cool part here, where I broke it down by Democrat, Republican, Democrat, and we basically saw like the by mail was really influenced, was really high in unaffiliated metro, unaffiliated micro, and then the COVIDs were really high with the COVID rates were really high with the, Democrat, Republican, while, your unaffiliated folks were, really, really low COVID rates, which probably, I'm sure someone can, speak to that better than I can. But I thought this was interesting here. But we see little stars right here. They call them A's right there because that's what this does. But explanatory value with statistical significance, and look what we have right there. Now the intercept, we don't look at that one, but look at everything else right here that contributes to by mail voting rates. So I want you to read this. I want you to kind of go through this. This has kind of been a labor of love for me. So we've got those. The other one we have is an Esri training. So the Esri training for week number 11, I'm pretty sure I've got it here. Uh-oh. Nice. Oh, here it is. Okay. Esri assignment number 3, I thought I put the date on it already. It's Intro to Regression Analysis using ArcGIS Pro. So just you go to your Esri training. Make sure you sign in. Yeah, that's me. And then I'm just going to literally go to my course catalog. Cut and paste this thing right in here. Introduction to Regression Analysis using ArcGIS Pro. And look, it asked me to resume the course because I've already started taking it. Okay, so you can go through, take the course. To me, reliable regression results, patterns of occurrence, spatial relationships on patterns of occurrence. And we'll get into a little bit of what we call geographically weighted regression. I'm not the best at that, or that we're creating new models for every single enumeration unit. So as you can imagine, that's going to be a local statistics as opposed to a global. And we'll kind of go from there. Any questions for? And then we got this here, and so just make sure you submit it. And I'll start looking at the assignments here in the next day or so that you submitted. So any questions for me?
You just went over this, but assignments for this week is Esri assignment and the reading, correct?
Yes,
those
that's
two?
correct.
Okay.
Yep. Yep, and I'll post an announcement tomorrow morning. Maybe if I have some time now, I'll do it, but post an announcement about deliverables and all that other good stuff when I post this up here.
And you said the position paper would be on December 3rd, was that correct?
December 3rd at noon, yes.
All righty, thank you, sir. Y'all have a good evening.
All right, see you all later. All right, sorry I couldn't join you in person here. These things come up, so I plan to be there next few weeks so we can finish strong. So I'll see you all later. Have a good day.
Yeah, thank you very
Thank
much.
you.
Take care.
Thanks. See you.
Good night.
Thank you.
All right.